Hello, so in this video we will talk about how to transform two random variables into one random variable, and we will start with the most popular like sum difference product in quotient for two random variables, and we'll start with the quotient of two random variables. So let's see what we have. We have an x which has a PDF of f of x, and we have y which is a PDF of f of y, and they are two independent random variables. And then we have z which is equal to x over y. So our question is how to find fz, right? So what do? We start with the CDF of f of z, which is equal to, because z is equal to x over y, so then this x over y is replacing the z, and then we integrate for all the values for which x over y is less than equal to z. Okay, why? Because we have a CDF here. Okay, so then how to find the probability of any range? We integrate it using that range for the joint probability distribution function. Now we can actually split it into fx and fy for this, because we have an independent case here, but for that for generalization we will leave it like this. Okay, so now note that if we have x if we have x over y less than z and y is greater than 0, then I can multiply y here and multiply by y here, and inequality will not change. So then this means then x is less than zy, correct? But if x over y is less than z and y is less than 0, then if I multiply by y here and multiply by y here, then the inequality will reverse. So then I will have x greater than zy. Okay, so this means that our integral, this guy will be split into two parts. Okay, so first part, I will write it again. The first part will be double integral uh, y positive 0 to infinity, and x, when y was positive, x was less than zy, correct? So then this is equal to minus infinity to zy, and then we have f of xy dx dy plus, then we have y negative. So y, this is equal to minus infinity to 0, and then what was x? X was greater than zy. So I will say x is equal to zy to infinity f of x y dx dy. Okay, now this is my expression for f of z. Okay, now this is f of z, which is CDF. Now we are interested in the PDF. So what do we do with this? This is equal to d over dz of f of z, correct? Okay, so now if I have to differentiate this integral, so let's take the first integral actually. So then we will have y is equal to 0 to infinity, uh, x is equal to minus infinity to zy fxy dx dy. In the first integral here, this value of z is only coming for x, right? So I can put this d over dz here. Okay, so then this becomes y is equal to 0 to infinity d over dz, or you can say partial d over partial dabba over dabba, but for the sake of this is clear that only x is, this is a partial integral here. So then f of this is minus infinity, okay, xy dy dx dy, sorry. Okay, Okay, now what? Now note that this guy here, now we are interested in this guy. Now this guy is equal to just y f of zy y. Okay, why can we say that? We can say that because of the fundamental theorem of calculus here, but let's do it here on the side. So let's say we have d over dz of minus infinity to zy f of xy d x comma y dx. Okay, so let's say the antiderivative of f is capital F. So this is equal to d over dz f of x y at zy minus infinity, correct? Which is equal to f of zy y minus f of minus infinity y, correct? Now if I use the differential in this second term, what will I get? I get a 0, correct? And if I apply this differential in the first term by the chain rule, what should I get? I should differentiate first of all this capital F, which will give me f of zy y, and then I have to differentiate this guy here with respect to y, with respect to z, and I will get what? I will get a y here. So that is why we will have this answer here. Okay, so coming back to 1, so let me erase this first. 1 integral of y is equal to 0 to infinity, and we'll have y f of zy y dy, and then we'll have a minus sign with the other one, y is equal to minus infinity to 0 y f of zy y dy. Why we will have a minus sign? Because for the second one we will have the antiderivative will be 0 for the first limit, and the antiderivative will be non-zero for the second limit, and for the second limit we will have minus sign, so that minus sign will come here. Okay, okay, so then this is my PDF of z, but we can combine it more, right? Now note that this is y is equal to 0 to infinity, so we have a positive y. This is y is equal to negative infinity to 0, so we have a negative y, so we will have a minus y here. So I can say plus here, I can say minus y here. Okay, so whenever y is negative, I have a minus y. Whenever y is positive, we have a positive y. So this is exactly the definition of the absolute value of y. So we can say minus infinity to infinity y and f of zy y dy. Okay, so this is my PDF of the quotient of x and y. Now what if we have discrete random variables? Then what? So then it's the same thing we will have in terms of our this. For example, if we go back to our first integral, first starting point, for this double integral, all we will have is we will have two sums here. But the only thing we will have to take care of is that if y is defined at the value of 0, then z will not be defined at that point. Why? Because z is equal to x over y, and if y is 0, then z is not defined. This is the only thing we have to take care of. Okay, so formally speaking, if we have discrete random variables and probability of z is equal to z, this is equal to summation of x, summation of y, p of x, p of y, this I'm considering independent here, where x is equal to zy. Okay, so all those values we sum for which x is equal to zy for a given z value, and we'll see an example right away. Okay, okay, so let's say we have x which is Gaussian with zero mean and some variance which is sigma x squared. And y we will have uh, again a normal random variable 0 and sigma y squared. Okay. Now again, what is our formula? Our formula says, we'll say f of z, this is equal to um minus infinity to infinity y f of x y xy dy. But this x is what? Zy. Okay. So all we have to do is we have to plug the values in this and simplify. Okay. And then you will see that it's nothing but simple integration. So then we will have this guy. We'll say minus infinity to infinity. What is f of x? F of x is 1 over 2 pi sigma x squared. X here, square root. And then we have e to the power of, uh, because it's zero mean, so we'll say minus of zy squared over 2 sigma x squared. Same thing with y, we'll have 1 over 2 pi sigma y squared e to the power of minus y squared over 2 sigma y squared. And then we have dy, correct? And then obviously we will have a y here. Okay. Okay. Now let's say what we can take outside here, outside the integral. Okay. Can we take anything outside the integral? Obviously we can take. We can take the square root. We can say 1 over 2 pi sigma x sigma y. This comes out. Okay. And then we can say minus infinity to infinity. This is y. And then we can say what? We can say e to the power of minus zy over sigma x squared, and actually half here, and then say minus half y over sigma y squared, and then dy. Okay, now my first observation is it an even function with respect to y or not? It is an even function because we have y squared term and absolute value of y term. So since the limits are from minus infinity to infinity, we can remove this 2, and start it from 0 to infinity. Okay, so this is the first observation here. Now what do we do is we say that our k is equal to what? Whatever is coming with y squared, we are calling it k. Okay, we can say k is equal to minus 1 over 2 z squared over sigma x squared minus 1 over 2 1 over sigma x squared. So 1 over sigma x squared. Okay, so then our integral becomes what? Our integral becomes 1 over pi sigma x sigma y, and we have just y here because we are 0 to infinity, and then we have e to the k y squared dy. Okay, now it's a simple substitution. Now we can say our t, this is equal to k y squared, which means dt, this is equal to 2 ky dy. Okay, so this means y dy is equal to, this means y dy this is equal to dt over 2k, dt over 2k, correct? Okay, so coming back here, we will have 1 over pi x sigma y, this is equal to e to the t dt, and then we have 1 over 2k here, correct? Okay, so what is this guy? This is just e to the t, which is equal to, what is t? t is ky squared, so then e to the ky squared, and then we have to plug in the limits again. So what are the limits? The limits are, if we go back to the integral, our limits are 0 to infinity. Okay, so then this is equal to, but let's put the value of k first. So what is our k? Our k is this guy, okay, which is a negative number. So we can say e to the minus half z squared over sigma y squared plus 1 over sigma x squared, correct? This was our our k, correct? Our k was z squared over this and 1, okay, so that is correct. So now if I put 0 to infinity here for, and then y squared, right? So then y squared here. So for 0 to infinity here, my infinity will give me 0 and my 0 will give me 1. So this is equal to negative 1. Okay. So then coming back here, so then what do we do? We are left with this term and we are left with this term. Okay. So my answer is just, so my final integral is what? 1 over 2k negative times 1 over pi sigma x sigma y, which is equal to my, what is 1 over 2k? So I will put the value of k here. So k is this guy, correct? So I can take this 2 on this side and then take the reciprocal of all of them. Okay, so then I should get z squared over sigma squared plus 1 over sigma squared. So z squared over sigma y squared plus 1 over sigma y squared, sigma x squared times 1 over pi sigma x sigma y. So this is my PDF of PDF of z. So this is my PDF of z. And if you want, you can simplify it more, and you can get some fancy answer. But this is not needed. I mean, the point is that you have to reach to this point. After that, it's just basic algebra. So now let's consider a discrete case. So now we have x, which is equal to geometric with some random variable p. Okay, which means that probability of x, this is equal to x, this is equal to 1 minus p x minus 1 to the p. Okay, which means that we are defining our geometric random variable in such a way that x is at least equal to 1. So x is defined only for natural numbers, correct? Okay, and then we have, let's say y is a Bernoulli random variable with parameter q, which means that and the support of y is 1 and minus 1. So probability of y is equal to 1. This is equal to q. This is equal to 1 minus probability of y is equal to negative 1. Correct? Now we are interested in probability of z is equal to x over y. Z is equal to x over y, and we are interested in probability of z is equal to z. Okay. Now note that if x is always positive and y is always either 1 or minus 1, so this means x can take any any integer except 0. Okay, because y is never 0 and x is never 0. So this is good because we are for discrete case we talked about that y cannot be 0, so then y is not 0, but then in this case x also cannot be 0 because of the way we have defined our geometric random variable. So that's why x over y is always can take any integer except 0. Okay, so this is the first thing. Now what is probability of z is equal to z? So if y is equal to plus 1, then this is equal to probability of x is equal to z times y is equal to 1, correct? So then this is equal to 1 minus p to the z minus 1 times p times probability of y is equal to 1 is q. Okay, so this is the case for y is equal to 1. So what is the case when y is equal to negative 1? So for this one, this means our z is less than 0, correct? Because x is always positive and x over y will always give me a negative number. So this means my probability of z is equal to z. This is equal to probability of x. This is equal to x is equal to minus z. Minus z because x is always positive and we said that z is negative, times probability of y is equal to negative 1. So this is equal to 1 minus p, 1 minus p, so we replace our z by minus z, correct? So we'll say minus z minus 1 times p times 1 minus q. So we can say probability of z is equal to z. This is equal to 1 minus p minus z plus 1 p 1 minus q when z is less than 0, and this is equal to 1 minus p z minus 1 p q when z is greater than 0, and it is equal to 0 if z is equal to 0. Okay, so this is my PMF of z, given that x is a geometric random variable and y is a Bernoulli random variable taking the values 1 and minus 1. So in short, what we did was we derived our PDF or PMF of a quotient of two random variables, and we did some examples to see how does this quotient is used in practice. So hope it was easy to understand, and thanks for watching. Hope you liked the video.